have a semiconductor material where we have done the doping. We know exactly how many uh, charge carriers are there, minority or majority. But ultimate goal is to move them. When charge moves, it's called current. But if there's no current flowing, there is still carriers which are moving under thermal energy. So they get every electron has some thermal energy which is making it randomly move around. Now, during the random movement, it is uh, going, but there's no net overall transport to any specific direction. So basically, this random movement would, okay, if you follow this, what happens, it's going in one direction, but then it has a scattering moment. And these scattering moment or this bouncing off are elastic. So there are few suppositions. Elastic mean they don't lose any energy, but they just change their direction. So again, there will be some bouncing and it changes direction. Again, some bouncing changes direction. So during these bouncing reactions, it does not have any specific overall movement in any x, y, minus x or minus y or z, minus z. There's no overall direction. But we see that there are bouncing off effects. So there is, unlike metals or unlike conductors, where in conductors we say electrons are always ready to move. You turn the voltage on, they start moving. Here we have an added figure of merit, that we have an added quantity that we are interested in, and we call that mobility. That how easy it is for them to move. Now, when you have these striking off, we can uh, we can just think about it that they have some dependence on temperature, because if you give them temperature, they would start moving faster, which means they would have more collisions. All right, more collisions means there'll be more uh, there'll be less movement in a way. I don't want to use exact word because we'll develop this understanding as we go. But right now, I just want to say that if you give more temperature, they'll move faster, which means they'll have more collisions, which means the overall movement will be more restrictive. Okay. But now it will have some effect on mobility. So the new term that we are introducing, mobility. So mobility will depend on the temperature. Now, if we apply an voltage to this system, and because of voltage, there's some electric field that generates. So that new electric field will cause these carriers to, they will still be going randomly, but there will be an overall effect that they will be moving in one direction overall more than other direction. If you make the voltage higher, they'll be still going randomly, but now the overall movement will be much more inclined. So from voltage, we have electric field that gets applied, and that electric field then results into overall movement. So now there are, when we apply the voltage and they start moving, we call that current to be drift current. That's the uh, type written here, drift. So it says carrier movement induced by a force of some type, right? Here in our case, the force is voltage. Now there is another movement which is, it's called diffusion. And diffusion is the example is like if you are in a room, large room, if I open a bottle of perfume, after some time you would also smell the perfume in the other end of the room. Right? How does how do you smell the perfume? What happens? How do this part of the room gets those vapors of the perfume to the other part of the room? That's a thing called diffusion. So the atoms or molecules uh, from higher concentration area, they travel to lower concentration area. And it's a concept which we talk about in potential energy also, right? So if you put something at higher height, it wants to, and if there is a pipe or something, it, for example, it's water placed on the higher level, it wants to travel to the lower level, higher height to lower height. But now diffusion is that carriers would move from one place with higher concentration to the place of lower concentration. So that's called diffusion. So then there are two types of current which make up the overall carrier transport. And those two things are called drift and diffusion. Without explaining, I have just written these two components of the current. So this is current density. So we write current like I always, but if you write current in one direction, current divided by distance, we write it as J. We will be using current density whenever we talk about devices. The reason is we want to make it independent of length. So current density, and here there are two things. N, current density of electrons in x direction. So, but we can write it a generalized equation also. But here we are saying this will have two components, drift and diffusion, right? We'll talk about these parts of this equation soon. But two components of current in devices, drift and diffusion. Drift is because of an external force, in this case, voltage, which causes electric field, or diffusion, which is concentration gradient, going from higher concentration to lower concentration, right? Now, Drude model of conductivity. It's a scientist who gave this, okay, how can we understand conductivity? More precisely, drift conductivity, the current which happens due to drift. Now, when they're moving, they have charge, which is written here. They, N is the number of charge carriers. We can write it Jn more to be more precisely because we are using N here. If it was holes, we would write P because we know N is the number of electrons, P is the number of holes. So anyway, so this is Jn, current density for electrons. Q times how many of those are there times what is their average velocity. These three things come together and they give us the current density. Now, here's the thing. The average velocity can be written as a multiple of mobility and electric field. So relationship, which I'm going to write separately, and you have to remember this because this is the fundamental relation that defines mobility. Mobility for n-type materials times electric field. This is what has been plugged in here to get this thing. And it's very easy to find. We know charge on an electron. We know how many electrons are there because we have done the doping. We can find mobility. We have the data on mobility and we have applied the voltage. So we know how much electric field is generated from that voltage. So we know all those four things. We know how much is the drift current, straightforward. Now, if there was no field applied, then this would, E would be zero. So in that case, if there was no, hold on, why this keeps on running away. If there was no field applied, this guy would be zero. This would be zero, and hence the total current would be zero, right? So going back to that first slide where they were randomly moving. So at equilibrium, which means no voltage, no electric field, hence no drift current. And when we apply the voltage, there is a net movement of electrons. So this is the equation for drift current. But I've already told you total current is component composed of drift current and diffusion current. But here we are just talking about applying a voltage, right? Now, this is particles moving, electrons moving. So we can apply Newton's equation also because it's a movement. They have a mass and they're moving. So then we can use the Newton's equations, and we know that final velocity equals starting velocity plus at, F equals ma, right? You remember those. So we're going to just modify them to our electronic states or electronic properties. So what we are doing is nothing different than that. And by and I will try to keep it simple for you. From acceleration, then we can find QE over M, right? Now, when we find average velocity, we say, okay, we replace a couple of things. We are using E tau here, which is the average time. And electron is moving, it's bouncing off. So what is the flight time? So we find that time by taking the distance covered divided by time. So that goes in there. And what we get is we get average velocity. The average velocity of an electron. So now we are using m star, which was effective mass, right? And we take the relationship of current. Now, current is dense. From previous slide, we take these factors, and these factors come together. We get a feature called conductivity. That's something new again here, thing called conductivity. So current is nothing but conductivity times applied field. Now, this is the relationship that we use because here we have applied the same relationship which we had for V average, which was equal to mu times field. When you apply these substitutions, we get this relationship for conductivity. This is a very important relationship. Conductivity is equal to Q n mu. And this is what we have applied here to simplify our current density equation. Right? Let me take you back to the previous page and then you'll see what we have done here. So this is the equation for current, and all we have done is we have taken this and we call this as conductivity, right? And from there, then we take the mobility and we plug in this relationship that we got here, and we get relationship that V average is equal to mu times E, or mu equals to V average over E. So let me rephrase again and put the important relationships in circle. This is an important relationship because this is what gives us the simplified version of drift current. This is a relationship because this gives us the value of mobility that has to go into this. And they all come together to give us overall drift current. Now, this relationship is different from what I showed you before. The first one I showed was overall current, which had two parts, drift and diffusion. Now, drift can have two parts, can have, because compensated material will have N-type and P-type dopings both. So if it does have, then you have to take care of N, mu N, and P mu P, both of those, N-type and P-type material. If one is negligible, then you use the simplified relation that was given on the previous slide, like this one, which is just relationship showing us electron current because we are using mu n and n on the other side. In the same way, we could have written current, then, hold on, let me finish there and I'll talk. I'm going to write mu, p, and e. Yeah, question. Somebody had a question? All right. Now, having the, knowing the average velocity, mobility, and conductivity. These are three new things which make up the current, drift current in semiconductor materials. So we don't use Ohm's law to find current. We have to use Drude model to find drift current, right? Now, in good conductors, we don't have to worry about mobility or have to worry about uh, field. You apply the voltage, no, we don't even have to worry about carrier concentration, right? Here we have to take care of all those things. Now, the difference here is that we take the electrons to travel in the opposite direction of the field. Hence, this negative sign. So, if you see the average velocity has the negative sign. We take velocity as a universally positive number, right? That's how we define velocity. But average velocity for electron has a negative because we want to clearly show that this is opposite to the field, which is part of this relationship. But when you take average for holes, that's going to be a positive number because it is taken in the direction of the field. Right? Questions? All right. So we built on top of this and we find, we calculate simply in a bar how much is the current because of drift. So there are, and you have questions and homework on this as well. If you have a bar of semiconductor material with length L, width W, and thickness T, and you apply voltage E, current I. Now you have to know the current because of electrons is taken in opposite direction. So this is the current electron current and it's taken opposite to the electric field. You may be confused because in circuits, we take the current to be coming out of positive terminal and going to negative terminal, right? And here I'm showing you something opposite. The difference is here we are talking about the movement of electron. That's it, movement of electrons. So when you talk about movement of electron, then it's taken in this direction. And we are talking about electronic current here. So in circuits, you talk about current. So those two concepts, don't get them confused. When you talk about electronic current and semiconductor devices, we take that to be opposite of the applied field or applied voltage. All right, so if you get these things in place and we take the whole motion in the direction of the applied voltage, we find basic relationships. And those relationships are R resistance is found as rho L over A. Now, and A here is area, and A is equal to W T. This is a fundamental relationship for resistance of a semiconducting material. What is rho? We haven't talked about rho. Rho is resistivity and it is 1 over conductivity. And conductivity we have seen on previous slide is Q. Let me just make sure I don't get it wrong. Q, hold on, let me. For N-type material, this would be Q N mu N. So fundamental electron charge, electron concentration, and electron mobility. We can find the resistance of a given semiconductor material with that. Right? Now, in this figure, when an electron enters, when an electron exits the material on this side, another electron enters the other side. The overall net number of charge carriers is always going to stay the same, right? So this is what is different in semiconductor material from metals or from conductors as well. The N or the charge carrier concentration cannot change. It doesn't change. So, or if a hole enters, in case of p-type material, then a hole leaves on the other side. So hence we can say that's the conductivity of the material. And from conductivity, we can find resistivity, and we plug in resistivity in this formula to find the resistance. All right. So remember this, for always for semiconductor material, this is how we find the concentration of the resistance of a material, of a semiconductor material. All right. Questions? To recap, we have seen this. I'm just again playing with the same concepts that Vx, here we have written average velocity as Vx, is related, that you can take this to the other side, or if you want to find mobility, then mobility is equal to average velocity over Ex. Now this is the average velocity of charge carrier. How fast are they moving, right? And we plug this in into this relationship of current density, right? Same thing. So, but this, you see the reference for the book in this relationship. Now, when we look at mobility, there'll be, if you are using n-type, we use mu n. If you are using holes, we use mu p. If we are talking about holes, we change minus Q to plus Q. So this relationship then become plus average velocity over field. So these are simple changes that go when you are going from electrons to holes in those relationships. And overall current, because of both of them, whether we have N type, P type, if it's compensated, they both will be there. If one is uh, dominant, then you just use, if it's N dominant, then you use only this part, you don't use this at all. If this is dominant, then you don't use this and you just write Q, P, mu, P, EX, right? Depending on whatever is the situation in the material. If it's clearly written, it's an N-type material, then you use just N portion of this equation. Now, mobility has strong dependence on temperature. So this is a relationship showing that when it's low temperature, the electrons would be striking with each other, scattering with each other, and that would be causing mobility to be less number. But when you ramp up the temperature, the mobility goes up, but up to a time when the charge carriers start striking with the lattice itself. So mobility then starts going down. So mobility is something that depends on temperature and it depends upon the carrier concentration. So this one shows that there is a dependence on time. So at lower temperature, the dominant effect on mobility, I want to use the word resistance to the movement of charged particle, but I cannot use resistance here because resistance is a very specific term. So that's why we say mobility is what helps us understand how easy it is for the carriers to flow. But it's a similar concept like resistance, but we cannot use the word resistance here. All right. So mobility is confined by the scattering between impurity particles by itself. But you ramp up the temperature, they start flowing much faster, mobility gets better, mobility gets higher. But if you keep on ramping, then the charge carriers start bouncing off the lattice itself. And lattice is composed of atoms in specific places, right? Crystal. So then mobility starts going down. If you dope it too high, then again, they start striking with each other, electrons or holes, mobility again goes down. So this is an interesting uh, plot. So this is nothing but I've blown up this one here for silicon and I've blown up the same thing here just to look at more closely. But this comes from the book itself. So what we are seeing is, so on y-axis is mobility, on x-axis is the impurity concentration. So what I'm showing here is that for silicon, for example, there is a certain level of mobility, but if you keep on increasing the carrier concentration, impurity gets degrading. So these are numbers 10, 19, 10, 18, 10, 70. Similar way, if you are if you have doped it with holes, the mobility gets degrading if you put too much of dopant in there. And it's a similar case for N type or P type for electron and holes for other materials as well. This gallium arsenide shows you similar behavior. Maybe it's a bit more constant for a longer region than silicon because silicon started, yeah, I think almost same. They started going down after that dramatically. And Germanium I put on the next slide. So germanium shows the same thing, that if you keep on adding impurity, you keep on going concentration higher and higher, mobility goes down. Again, mobility goes down means overall current goes down. So if I go back to this relationship, we have to remember why it is important, because overall conductivity of your devices will go down if you dope it too high. So there's this thing, this goes up, this goes down. So mobility has then direct impact on the conductivity, on the uh, current or the current density. All right, now one can say I can keep on ramping up the voltage and the average velocity can keep on going up. Well, so we can have high conductivity, right? Because mobility was dependent on uh, average velocity. But that's also not the case. There is a rollover in the voltage, rollover in the current, because the drift velocity becomes constant. It cannot go above certain limit. So far we say in conductors, we say you keep on ramping up the voltage, the current will keep on going higher and higher. Electrons will start moving much faster. And in semiconductor devices, it's not the case. We see that the drift current is not a function of voltage. It's not a function of only the voltage. There are other things that are part in there. So when, and this is for silicon, at higher, this plot is for silicon. At higher electric field, and especially that number is 10 raised to power 3 here. You have to remember this number also, because if you are given bigger number than this, you cannot, you can use this number as the average velocity, 10 raised to power 7. For a field of more than 1000, the average velocity becomes saturated. Average drift velocity becomes saturated. So drift velocity then reduces the overall drift current density. So now if I take you back on this also, you would see that mobility has dependence over average velocity, average drift velocities. But so if average drift velocity becomes saturated, cannot keep on going up with field, which means this also has an upper limit of how much it can go because of this guy again. So now when we talk about this region, this is high field effect or hot carrier effect, where the drift velocity reaches an upper limit near 10 raised to power 7 meter per centimeter per second for silicon. And in this case, the extra energy that you are providing from outside through the voltage is just being transferred to the lattice. It's just getting wasted there. All right. So where do we use that? So this is an example from the book. It's the question gives you a few things. So the question says a silicon material with cross section area. It gives you an area. It gives you the doping concentration, and it says it's donor, it's N type. It has a resistance of 90 ohms. It says giving you resistance also. So this relationship rho L over A, it has given us many things there. The saturation velocity of electrons, silicon is 10 raised to power 7, which means if we find the field is more, then we'll just use this number. Otherwise, we have to go to that previous plot and find the number of the average velocity. Calculate the electron drift velocity if you apply a voltage of 100 volt across the piece. Now, voltage is equal to, sorry, the field is equal to applied voltage divided by the length that it is applied for, right? So if it tells you it is 100 volt, we find the field, we say, okay, what's the length of the material? So length is given 2 centimeter. So I need to write centimeters. So I write 2 times 10 raised to power what? Minus 2, right? So when all said and done, we get the field to be this guy. Now this field is bigger than the saturating field, which was given that if this is the field, then the saturation velocity is this number. So we can use VD as this number. All right. So a few things. Now let's start solving what is given and what's missing. So we know resistivity is 1 over conductivity, and we know conductivity you can find like this, and we have everything. We know the electric charge, electron charge of 1 electron. We know the mobility. Oh, we don't know the mobility. Mobility is what we have to find from here. So here we don't know this, but we know this guy and we know this guy. So you plug in that here and we get the mobility. Okay, I have left this without answer because I'm showing you the steps and I expect you to do those steps and find the answers. So field, we have this, and for this field, we have this drift velocity. So we have these two, we can find this guy. Once we find this guy, we plug it in here, we find this guy. When you find this guy, we plug it here, and we have everything available in this relationship. Now, current. We have used this J equals before, but when you have to find just the current, I told you this was divided by area. Oh, I said length before, sorry. So this was current density, which is current divided by area. So if you just have to find current, all you have done is modified this relationship, but you have multiplied this side with current. Sorry, the area, not the. So to find, instead of current density, we are finding current, so we have multiplied this with the area on this side. So that gives us the exact answer on what is the current through the piece for that applied voltage. I'm sorry about the lines, but if you follow the recording, you can go through which line was going where and how do we solve this kind of questions. All right, so the other part, diffusion. We haven't uh, gone through diffusion a whole lot, but the relationship for diffusion is also straightforward. There are 3 parts to it. One is the charge concentration, the charge itself, Q. The other thing is diffusion coefficient, which is a constant. Diffusivity constant or diffusion coefficient. And how much is the change in concentration over the distance across which we want to find the diffusion current. So 3 parts to it. Fundamental electronic charge, diffusivity constant, and what is the rate of change of concentration across the length on which we want to find the diffusion current itself, right? So this will again be given, for example, it will be given maybe carrier concentration of say 10 to the 20 in one part, and they say 2 meter away it becomes 10 raised to power 15. So you have 10 raised to power 20 minus 10 raised to power 15 divided by the distance that you have to find it. So that would be the rate of change of the carrier concentration across a specific distance, right? So we plug in three values and we can find diffusion current. So here again, this is showing this diffusion current for electrons over X distance. Now, is another interesting thing that diffusivity or diffusion coefficient has a constant relationship with the mobility. And that relationship is called Einstein's relationship. You need to remember this also, because if you are given mobility, you can find diffusivity constant. If you're given diffusivity, you can find diffusion coefficient. So if you're given diffusion coefficient, you can find mobility. If you're given mobility, you can find diffusion coefficient. And that relationship is, I remember it by d over mu equals kt over q. It rhymes. D over mu equals kt over q. So respective coefficient, respective type. For n type, dn over mu n equals kt over q. And this is always 26 millivolt. 26 millivolt, or you can write 0.026 millivolt. Sorry, 0.026 volts. Another important relationship called Einstein's relationship. Easy way to remember, d over mu equals kt over q. Just make it rhyme and you have your relationship. Why we use it? Kt over q is a constant. It's 26 millivolt. If you know the mobility, you can find out diffusion coefficient. If you know the diffusion coefficient, you can find the mobility from that. All right? Questions? All right. If there are no question, I'll stop here. This is, these are the simple, straightforward relationships, a few, 7, 8 of those, which we use to find exact current charge transport in any device, right? Just a side note, for diffusion, one can say, okay, if you have doped a material, why would there be high concentration in one place and low concentration on the other place, right? It's a same device. So that's where you can have an excess carrier concentration maybe by shining light in one part, right? Or maybe there may be an introduction of charge carriers using a voltage source. So there can be multiple ways why you can have a very limited region, higher spike in carrier concentration. Mostly we do it with optical materials where you shine light and there's a localized increase in carrier concentration. We call them excess charge carrier. And that's next module.